In physics, we use the same convention for positive and negative as you do in maths for plotting coordinates on a coordinate grid. So in maths, you are used to having a horizontal x-axis which goes from negative numbers to the left and then your positive numbers to the right. So this is transferred to physics so that anything going to the left is said to be negative and anything going to the right is said to be positive. Your y-axis in maths, that goes from positive numbers upwards and your negative numbers are downwards. So in physics we say that anything going upwards has got a positive value and anything going downwards has got a negative value. So in the situation with the motorway shown there, we've got a car which is travelling at 30 meters per second south. So because south is downwards on the points of the compass, then we can say its velocity is minus 30 meters per second. The van, on the other hand, is travelling north, which is the positive direction, and so we'd say that has got a velocity of plus 30 meters per second. In practical terms, we can speed up a car by pressing the accelerator pedal, which is the one on the right. And this causes the engine to transfer energy from the chemical store of the petrol, diesel, whatever fuel you're using, to the kinetic store of the moving parts in the car. And then through the gearbox and through other bits of the car, that force, the greater force, is transferred to the wheels. In order to slow the car down, you press the brake, which is the middle pedal, and they will then apply a force onto the wheels, and this time energy is transferred from the kinetic store of the car to the thermal store of the brakes, and the car will slow down. So in order to change the direction of the vehicle without changing the speed, you would use the steering wheel, and that transfers a sideways force to the wheels. Now the bit in the second half of this slide is very, very important. You need to learn this one and be able to apply the principle to different situations. So first of all, in physics, a change in velocity is called acceleration. Now, if a resultant force acts on an object, the velocity of that object will change. So if the object is standing still and a resultant force acts, that object will begin to move, which means its velocity has changed from 0 meters per second to something meters per second. If the object is already moving and a resultant force acts, then the velocity would change from what it was to a new velocity. If they press the accelerator, that velocity will have got greater. If they press the brake, that will create a backwards resultant force and the object will slow down. Another way of saying this is if a resultant force acts on an object, the object accelerates. In order to speed up your skateboard, you simply kick along the ground, and that transfers energy into the kinetic store of the skateboard. In order to decrease the speed of the skateboard, you could use your foot and drag that along the ground. You could tilt the skateboard backwards so the back of the skateboard drags on the ground, or you could roll the skateboard into a rougher surface, for example into some grass or some gravel, Now in all of these cases you are increasing the frictional force acting in the opposite direction to your travel, and so energy is transferred from the kinetic store of the skateboard to the thermal store of the surface. As far as a tennis ball is concerned, you can change the speed of a tennis ball using your racket by as the ball hits the racket, you pull the racket backwards slightly in the direction of the travel of the ball, and that will slow it down. What's happening there physics wise is that energy is being transferred from the kinetic store of the tennis ball into the elastic store of the strings of the racket. Of course, at the same time you're exerting a force on the ball. The same thing will be true for direction of the tennis ball. You are transferring energy from the ball's kinetic energy store to the elastic store of the strings, and then transferring it back to the ball's kinetic store again as it goes in the opposite direction. So things will accelerate if a resultant force is acting. So we're looking at these diagrams and asking ourselves, is there a resultant force? If there is, then acceleration will occur. In A, we have a vector force downwards of 20 newtons and a vector upwards of 20 newtons. The upwards is positive 20, the downwards is minus 20. Add those together, you get 0. No resultant force, therefore that will not accelerate. B, you have two forces here of 20 newtons at right angles to one another. This time there is a resultant force which will be diagonally between those two forces, therefore that object will accelerate in a southeasterly direction. Let us say you have two forces acting downwards, each of 20 newtons. So the resultant of those two will be 40 newtons, because they're acting in the same direction. C will be experiencing a resultant force downwards, and therefore it will accelerate downwards. D, we have a lorry going along at 20 meters per second. The forward force is 20 newtons, and then we've got frictional forces acting against it of 200 newtons. Add those two up, because they're equal and opposite, they will give you 0. So in this situation, the lorry will not accelerate, it will keep going at 20 meters per second. Finally, E, same lorry going at 20 meters per second, this time experiencing a frictional force of 400 newtons. If you add the two forces, you're going to end up with 200 newtons to the left, so that would be minus 200 newtons. So that lorry will experience an acceleration, and as a result of that resultant force, it will slow down. The unit of acceleration is meters per second squared. And it's important that you understand what this actually means. So if something has an acceleration of 2 meters per second squared, it means that each second it's getting 2 meters per second faster. So after 1 second it will be going 2 meters per second. After 2 seconds it'll be doing 4 meters per second. After 5 seconds it'll be doing 10 meters per second. So it's simply going up 2 meters per second each second. So another way of saying it is 2 meters per second squared means the same as 2 meters per second, or 2 meters per second each second. In the symbol version of the equation here, you'll see the use of a triangle before the V. This triangle is the Greek letter D, it's a capital D, delta, and it's shaped like that because that's the shape of a delta, the Nile Delta for example in Egypt. It's triangular. In maths and science, this is conventionally used to mean the change in. So if you see a triangle like that, that means change in. So the delta V would mean the change in velocity. So having a look first at the data for car number 1, you'll see there at the start it's not moving at all. Then after 2 seconds it's now going 5 meters per second. That then goes up consistently 5, 10, 15, 20, 25, and this is shown on the blue line on the graph. Now if we apply our formula, which is the change of velocity divided by the time taken, so if we take that car between any of those 2 second intervals, the velocity is changing by 5. So the velocity change 5, the time taken 2, 5 divided by 2 gives you 2.5 meters per second squared. Car number 2, you'll see there has gone from 0 to 6 in 2 seconds, and then to 12, and then to 18, but then it has stopped getting any faster. So it's now going at a steady speed, it's stopped accelerating. This is shown you on the graph on the orange line there. And again, applying our formula, it's the change of velocity divided by the time. So the change in velocity would be 6. The time taken for that change would be 2. So you've got 6 divided by 2, so it gives you 3 meters per second squared. Which means that the maker of car 2, making the claim that their car accelerates more, is actually correct. They're accelerating at 3 meters per second squared. Car 1 is accelerating at 2.5 meters per second squared. First set of questions, the units are all meters per second squared because it's asking for accelerations. A will be 2 divided by 4, giving you a half. B, 5 over 2, giving you 2.5, 2.5. C is 20 over 5, giving you 4. D will be 8 over 4, giving you 2. E is 14 over 18, giving you 0.7 recurring. F is 34 over 4, giving you 8.5. G, 12 over 9, giving you 1.3 recurring. H is 2.8, which is, 2 over 8, which is 0.25. I is 56 over 3, which is 18.6 recurring. And finally J is 221 divided by 12, which should give you 18.4. The second batch, you had to rearrange the equation from acceleration is change of velocity over time to time equals change of velocity divided by acceleration. So the units for all of these will be seconds. A is 4 over 2, giving you 2. B is 30 divided by 5, which is 6. C, 72 divided by 8, which is 9. D, 32 over 5, which gives you 6.4. E, 26 over 6, giving you 4.3 recurring. F is 5.5 over 1.1, which gives you 5. G is 7 over 7.2, giving you 0.97. H, 6.2 divided by 4, giving 1.55. I is 160 divided by 2, so divided by 20, beg your pardon, which equals 8. And then finally J is 16 over 30, which is 0.53. Last block, first 4 are accelerations, so they're all going to be meters per second squared. So first one, 2 over 40, it gives you 0.05. B is 2 over 0.5, so it gives you 4. C is 15 over, now on this one you've got to change the minutes to seconds, so 2 minutes to seconds, that's 120. So you're going to have 15 divided by 120, which is 0.125. And then D, we've got 73 over 12, which is 6.08. Letter E, we've got a how long, so this is going to be the change of speed divided by the acceleration. 2.3 divided by 4.5, giving you 5.1 recurring. Next one, you should work that through, it will come to 45 over 9, which is 5 seconds. For G, you've got 28 divided by 5, so that's 5.6 seconds. And then finally, the most difficult one here, you've actually got to convert kilometers per hour into meters per second. So to do this, you first of all convert your kilometers to meters. So 120 kilometers is 120,000 meters. So that's 120,000 meters per hour. Now an hour is 3,600 seconds. So if you take your 120,000 divided by 3,600, it will give you 33.3 recurring meters per second. Okay, so that's just about 70 miles an hour. So we're now doing an emergency stop in 3 seconds. So we've got the change of speed is going to be from 33.3 to 0, and we're going to divide that by 3, and that gives us 11.1 recurring meters per second squared. That's the deceleration. What was the car's average velocity? Well, the starting velocity was 33.3 recurring. The final velocity was 0. So we have to take those two, take them away, that gives us 33.3 recurring, and then divide by 2 to find the average, and that gives us an average velocity of 16.6 recurring meters per second. And then finally we get to the stopping distance. So we know that the velocity is the distance divided by the time, which means that distance is velocity times time. Velocity we worked out was 16.6 recurring. The time was 3 seconds, so that gives us 50 meters for the stopping